Sulfur trioxide decomposes on heating to form an equilibrium mixture containing sulfur dioxide and oxygen. A sample of sulfur trioxide was heated and allowed to reach equilibrium at a given temperature. The equilibrium mixture contained 6.08 grams of sulfur dioxide. Calculate the mass of oxygen in the equilibrium mixture. So if we think about what's happening here, for every sulfur dioxide, we get half as much oxygen. So if we're getting 6.08 grams of sulfur dioxide, which has an MR of 64.1, so we can do that on our calculator into moles, 0.0949, then we would get half as much because the ratio is 2 to 1. So the moles of oxygen would be this divided by 2. So 0.0474. And so the mass of oxygen would be mass is Mr. moles, so times by the MR, 32. I've kept all this on my calculator throughout the calculation and I'm getting 1.52 grams. A different mass of sulfur trioxide was heated and allowed to reach equilibrium. And then they've given us the amounts at equilibrium. They've given us the Kp value. And they've asked us to calculate the mole fraction. Well, to calculate the mole fraction, you need the total moles. So the first thing I would do is add up the total moles. So just add them up, 0.32, 1.2, 1.6. So we're getting a total moles of 2.12. And therefore the fractions of each, we're going to do the first one, 0.32 divided by 2.12. So that's coming out as 0.151. Then we're going to do 1.2 divided by 2.12. And that is coming out as 0.566. And then we're going to do 0.6 divided by 2.12. And that is coming out as 0.283. Okay. It then wants us to calculate or give an expression for Kp. So an expression for Kp, remember it's the partial pressures of the products over the partial pressures of the reactant. So it's the partial pressure of SO2 squared. And then just remember, if you're going to use any brackets, don't make them no squared brackets, rounded brackets. Partial pressure of oxygen over the partial pressure of sulfur trioxide squared. And then it wants us to calculate the total pressure for this reaction. So this is now some algebra. We know the value of Kp is 7.62 times 10 to the 5. And we know that partial pressure is mole fraction times total pressure. So we know that we've got 0.566 times whatever this pressure is squared. And then we've got 0.283 times this pressure. And then we've got 0.151 times this pressure squared again. So if we do some algebra on this, if we do 0.566 squared, we get 0.320, and then we do squared p, we'd get p squared. And then we're going to times that by 0.283 times p. And then again, if we do the same on the bottom line, 0.151 squared, this comes out as 0.0228, and then square the p is p squared. What we can do now is notice that we can cancel the p squareds, and that leaves us with a bunch of numbers and 1p. So I'm going to rearrange. If I keep p where it is, so I'm going to leave this where it is, move everything else away. So the 7.62 times 10 to the 5 was already on the opposite side to the p. I'm going to times out the bottom line, so times both sides by 0.0228, and then I'm going to divide both sides by 0.320 and 0.283. And I can type that into my calculator. And I'm getting an answer of 1, 9, and we don't need to keep all these significant figures off my calculator. I'm going to go 192 and 3 noughts, or, and that would be in kilopascals because the kp was in, oh no, it's in pascals, sorry, because the kp was in pascals. You could write that in standard form as 1.92 times 10 to the 5. For this reaction at 1050 Kelvin, the value was 7.62 times 10 to the 5, and at 500 Kelvin, the value was lower. So, as temperature decreases, Kp decreases, so equilibrium shifts left with decreasing temperature, because if Kp goes down, then we must have shifted away from the products. When temperature decreases, equilibrium shifts in the exothermic direction to oppose the change. So left or backwards is exothermic, which means forward is endo. Now you could obviously do the reverse of this and say as the temperature increases, Kp increases, so the equilibrium shifts right with increasing temperature. When temperature increases, equilibrium shifts in the endothermic direction to oppose the change, so forward is endothermic. Obviously, that is all the exact same answer, just the converse version. Use data from 7.3 to calculate Kp at 500 for this equation. Now, remember in that, let's just remind ourselves that this was for the equation right back here, 2SO3. So 2SO3 in equilibrium with 2SO2 and O2 had a Kp at 500 of 3.94 times 10 to the 4 pascals. What we've got here is the reverse, it's not the reverse, it's just the half the moles, half the moles of what we had originally. And therefore, if it is half the moles, remembering that the moles become powers, we are going to need to raise 3.94 to the power a half or square root it. So you could actually on your calculator just do this to the power a half, or you can square root the answer. Now, if you do either of those, you're going to get 198.5. And the units, given that the units for the Kp, if you look before, were pascals and we've square rooted it, they are pascals to the half.